In this first part of Chapter 16, we're going to talk about electric potential energy and get into then next time electric potential and eventually capacitance. Now, electric potential energy is very similar to gravitational potential energy. Here I've set up a system of a proton and an electron, or a positive charge and a negative charge, because this is going to be an attractive system, just like gravity is attractive. And so when I pull the negative charge away from the positive charge, we're going to actually increase the energy, because the negative charge is going to want to come nearer to that positive charge. And so when I do the opposite of what the system wants to do, then that is going to take work and add energy to the system. So therefore, as I move the negative charge away from the positive charge, the amount of energy is actually going to increase, just as if I move two masses apart, we're going to increase the amount of potential energy. So the formula for potential energy that we learned in the fall was it's the universal gravitational constant times the product of the masses just divided by r. Notice that the square has disappeared. That was there for either the field or the force equations. And for gravity, there's a negative sign here indicating that the force is attractive, and that means when I increase r, the energy is going to increase as well. You notice that there is no sign in the electric potential energy equation, because it kind of depends. It could be attractive or repulsive. So, and there's no absolute values here. So if I have opposite signs on my charges, then I'm going to end up with a negative sign. I'm going to end up with an attractive force in a case where the energy increases as we pull these things apart. Whereas if they are the same sign, then the sign is positive and the energy will actually decrease as I decrease r. And for the potential energy, generally we're going to give it the symbol U. I'm not sure why your book uses PE for gravity in the fall, and then we switched to U for electric energy, but U is actually in the more common form. And so as all field forces, these are conservative forces, and so it can do work on the system. In the electric field, it's particularly important to acknowledge that there are several places where there are the same energy, and so we're going to call these equal potential lines, and we're going to get into more of what a potential is next time. But we can draw these same lines around a gravitational system, where these are lines where we have the same amount of energy. If I were to put a test mass in here, it would have the same energy no matter where I put it on this ring. The same is true for the electric field, is that we can draw circles where there is, if we put a point charge, it would have the same energy all the way around. So the shape gets more complicated the more objects we add to our system, but for a single object, it's just a sphere. So what does this mean is that potential energy can be stored in the electric field. This is one way to make batteries, and the energy depends only on the location, just like it does with gravity, not on the path taken to get there. So we define the potential energy at some reference point as being 0, just like we do for gravity. And then it's not really 0 until our two charges are at infinity. So what does the formula look like? So if we have a proton and electron initially separated by some distance r and are brought closer together, how does that change the potential energy? So again, we end up with a negative sign here. So I'm going to pull that out, and we're going to end up with E squared, because presumably we have a single proton and a single electron where the amount of charge is equal to E. So if we bring them closer together, then the energy decreases. So we're going to get a number less than 0, just like we did when we looked at this for the potential energy due to gravity. So the negative sign indicates the energy will decrease as we bring those charges closer together. And another handy unit to use instead of joules for energy is the electron volt, because often we're going to be talking about very, very, very small amounts of energy if we're going to deal with a single proton or an electron. And so an electron volt is defined as 1.6 times 10 to the negative ninth joules, because that is what E is. That's the number for E, so it's a handy number to talk about. So the electrons in a normal atom have energies in the tens of electron volts. Excited electrons then have thousands of electron volts, and high energy gamma rays have energies in the millions of electron volts. So it's a handy unit when we're talking about very, very small amounts of energy. Now when we're dealing with systems of charges, we need to basically use our superposition principle and be able to add up the energies. So if we had a system of charges where we had 3 charges and we want to figure out how much energy is in the system, we can basically start out with 1 charge, keep adding charges, and add up all the pairwise interactions. So, for example, if we start out with a single charge, the energy is 0 because there's no second charge. Then if we add a second charge, then the system now has energy related to the distance between those 2 charges and the product of those charges. Now if we add a third charge, it actually adds 2 terms to our system because we're looking at the pairwise interaction between 1 and 3 and 2 and 3. And we need to take into account those charges and distances as well. But once we figure that out, it doesn't matter what order we do things in or what the orientation is, as long as all the distances remain the same, that we can do the math either way. But for an example, we're just going to calculate this system where we have 2 charges, and I'm going to give you a few minutes to figure out the amount of energy in this system, which is the 2 protons in a uranium atom are very close together. So how much energy is in the system of just 2 of those protons? Okay, hopefully you took a minute to figure that out, and we're going to convert that also to electron volts, because it's going to be a little bit easier number to deal with than the number we're going to get in joules. So the formula is KE_Q1 times Q2 times R, where both Q's are a single proton, so they're 1.6 times 10 to the negative 19th. So the energy in the system is R Coulomb's constant, 8.99 times 10 to the 9th Newton meter squared per Coulomb squared, times E squared, 1.6 times 10 to the negative 19th coulombs squared. It's not multiplied by 2, since the 2 are multiplied together, they're not added. So this is equal to KE E squared over R, not times 2. I see people often multiplying that by 2. Sometimes I even do it, so just be careful on that. And so we get 3.8 times 10 to the negative 14th joules. And if we divide that by the conversion to electron volts, which is the same as the coulombs, so negative electron volts per joule, then we get 2.4 times 10 to the 5th electron volts, or 240 keV. Now that is a lot of energy, and it's repulsive since those are both protons, but they're held together in the atom by a force we're not going to talk about, called the strong force, which binds all nuclei together but needs to overcome the electrostatic repulsion.